So we are now ready for answering the question after all this warm-up. We know CL is equal to CL naught plus CL alpha into alpha plus CL delta E into delta E. Similarly, CM we know CM naught plus CM alpha into alpha plus Cm delta E into delta E. Now think of if I am trying to go to a trim, some point here. What is the condition here? Condition is this point corresponds to CL trim, correct? And also this point where Cm equal to 0. I am asking, suppose the airplane initially was flying here at this point. I am asking a question. I want to fly at point 2. How much elevator deflection I will give and which direction? Let's say this was the initial point where delta requirement was 0. So everything Cm naught came because of the airplane design. So that is the question you are asking. Now from 1 CL to I am going to a CL corresponding to point 2, then what is the elevator deflection I should give? Final question is it at all flyable or not? Okay. So since I know second point or first point, it has to be in trim, that is Cm has to be 0. So I write 0 is equal to Cm naught plus Cm alpha into alpha trim plus Cm delta E into delta E required. If I revisit CL, the CL will become now CL trim this is equal to CL naught plus CL alpha into alpha trim plus CL delta E into delta E required, right? For simplicity, let us assume that this value is 0. You can always use this value and write the expression. That's not a big problem. So using this CL trim equation and Cm equal to 0, I can write delta E equal to minus Cm naught CL alpha plus Cm alpha CL trim divided by Cm delta E CL alpha minus Cm alpha CL delta E. Okay, this is what? Don't forget, this is delta E required. For what? Delta E required for a particular CL trim. What is the information required? I need to know Cm naught of the airplane, I need to know CL alpha of the airplane, Cm delta E of the airplane, and CL delta E of the airplane. If I know, then immediately this expression will tell me if I want to fly at CL trim 0.6, what is the delta E required? Correct? That is what is our aim. But now I am trying to give some designer feel to this expression. So we'll do some manipulation, some approximation. Let us see what we do. We divide numerator and denominator by CL alpha. Then what we'll have? We'll have minus Cm naught minus Cm alpha by CL alpha into CL trim divided by Cm delta E minus Cm alpha by CL alpha into CL delta E. Okay. We do further approximation that this term, you see actually when you put number, this term is less than this. This is typically Cm delta will be of order of minus 1. Cm alpha by CL alpha is order of 5 or 6. The CL delta is around 0.6, 0.7. So indeed, this will be lesser compared to Cm delta E. So it's not a bad idea to neglect this to get a designer's perspective. So if I neglect this term compared to Cm delta E, then I get a neater term which the designer can get a better feel. So I have delta E required equal to minus Cm naught by Cm delta E minus dCm by dCl, Cm alpha by Cl alpha, which we are expert now. Is it clear? This is Cm naught. What we have done? This Cm alpha by Cl alpha into Cl delta E. This is less than Cm delta E. So this has gone. So minus Cm naught by Cm delta E is here. Then Cm alpha by Cl alpha dCm by dCl. This is here. Cl trim is here. Cm delta is here. What is the meaning? The meaning is, tell me what Cl you want to trim, then immediately this will give delta E required. But then, you know, if delta required is coming 50 degrees, 45 degrees, you say, oh, sorry man, I cannot trim your aircraft at that CL because delta is coming very, very high. Okay, so there is a limit that will be set by this. For what is this dCm by dCl? This is nothing but static margin, remember? And since this is negative, this dCm by dCl is what? This is minus static margin, so this is negative. And Cm naught is positive. Let's understand this. Cm naught is positive, Cm delta is negative. You know, if this is the tail, this is the elevator, CG is somewhere here, and delta E positive we have defined as down. If you check the note, this delta E down will give additional lift here, which will give nose down moment about CG. So we say Cm delta E is less than 0. It is negative. For a positive delta E, there is a negative Cm. Okay. So this is negative, this is positive. So this is, whole term is positive. dCm by dCl is negative for a statically stable airplane. So I write negative. This is also negative. This is positive. So this part is negative. So I write it like this. I write delta E required equal to delta E naught plus d delta E by dCl trim into Cl trim. And what is d delta E by dCl trim? This is nothing but whole of this expression including minus sign. Okay? That is minus dCm by dCl by Cm delta E. So now if I plot delta E versus Cl trim, what type of graph I will get? I will get some delta E naught, and the slope will be negative. D delta E by dCl trim, you could see, is nothing but minus dCm by dCl by Cm delta E. Cm delta is negative, this is negative, negative positive, this minus sign is there. So this term, which is d delta E by dCl trim, is negative. So I will get some line like this. Okay? And that will be corresponding to a particular CG location. Why? Because dCm by dCl is here, which will change with CG location. Where dCm by dCl is minus static margin, and as CG goes aft, the static margin reduces, so this becomes lesser and lesser negative. Okay? So as I am going back, I am taking HCG, let's say earlier it was 0.1, here it's 0.1, now 0.2 means I am taking it back. So this is HCG equal to 0.3. What is the message you are getting? That if I am trying to trim an aircraft at different CL, delta E requirement will go on increasing as static stability is increased. Let us understand this point. Good morning, friends. We are at a very important juncture now. We have understood a little bit about static stability. We have understood what is the trim point. We have understood what is static margin. And we have also understood what is the effect of CG in terms of stability, how it affects stability. And more importantly, we have also understood how do I get the neutral point of the airplane. Now the question is, as repeatedly I am been telling, if an aircraft is highly statically stable, then you need to put a lot of effort to take it from one trim to another trim. That is, if it is flying at a particular angle of attack or particular CL, if you want to change the CL, let's say I have to increase the CL and lower the velocity so that it's still lift equal to weight. So if I want to increase the CL, I have to increase the angle of attack, and I have to give a nose-up moment, and that could be done through elevator by putting the elevator up. And we are trying to find out how much elevator up I have to give to change CL from one CL trim to another CL trim. And it goes without saying, we understand if an aircraft is highly stable, then we have to put a lot of effort to change its equilibrium from one trim to another trim. That means we have to give more effort. More effort means it has to come through the elevator. Okay? So we'll try to establish this and extract whatever a designer should have in his mind while he is designing an aircraft. So if I simply revise few things, few important things which you need to understand clearly before I try to synthesize all this concept. One is, every time I am drawing this graph, Cm, and this Cm is pitching moment coefficient about center of gravity of the airplane. This is Cl, and we know by now whether it is Cl or alpha. It's a question of a scale factor. And if I say an aircraft is statically stable, that means the dCm by dCl, the slope is negative about the equilibrium point or the trim point. Okay? If we try to visualize, it actually means the aircraft is, let's say cruise is our equilibrium point. This aircraft is here where lift is equal to weight, thrust is equal to drag, and this is one equilibrium, right? And when I have drawn Cm versus Cl, the slope is nothing but dCm by dCl. The slope is nothing but minus static margin, and static margin we have understood to be the distance between neutral point and center of gravity of the airplane. That is, if this is the CG of the airplane, and if this is the neutral point, I write NP, then this distance is the static margin, and which is non-dimensionalized with respect to the mean aerodynamic chord. Static margin is expressed in a non-dimensional form, and you know that we non-dimensionalize static margin by mean aerodynamic chord. That is, if this distance physically is x, then x by c bar is static margin. Okay? What we also understand that this static margin is a unique number for a given configuration for a particular CG location. Correct? You can understand from here, if this is the CG of the aircraft and the aircraft is same, but for CG if I change by distributing the internal components, then as CG moves towards neutral point, this separation reduces, so the slope of the line also will reduce. It will become more flatter, and also physically you understand if the separation reduces, so there is a reduction in the static stability. And at a point, very clearly when CG coincides with the neutral point, it is neutrally stable. So there is no restoring moment. Okay, this is, we understand. Now, what is the question we are going to ask ourselves? Now we are focusing on the control. Meaning thereby, suppose the airplane was flying here, now the airplane wants to fly here. Let's say point 2. How much elevator deflection should I give to ensure that the airplane is now flying at trim, that is at lift equal to weight, thrust equal to drag, thrust lift equal to weight, thrust equal to drag, but at different CL. But you know, since this is statically stable airplane, the moment you try to change the equilibrium from here to here, because it is statically stable, it will generate an initial tendency to come back to the original equilibrium. And from the graph, how do I read that? If the CL, new CL is here, then the airplane will generate negative pitching moment. Negative pitching moment means the angle of attack will have a tendency to come down, and that is what we say it has a tendency to come back to the equilibrium. So it's a statically stable. It is very well-known characteristic of a statically stable system. But what is our aim? Our aim is, no, we will not allow it to come back. We want to hold it here. So if I want to hold it here, what I have to do? Who is trying to take it back? This negative moment? So if I want to hold this here, means I have to nullify this negative moment. So how can I nullify this negative moment? So there is an elevator here. So I have to do what? I have to generate positive moment, positive pitching moment. And how can I generate positive pitching moment? I will deflect the elevator up. And because of deflection of elevator, there will be a force generated at the horizontal tail in the downward direction, and this will give a nose-up moment, and I should be smart enough to get appropriate deflection so that this moment and the restoring moment, they cancel, and again it becomes a trim point, that is Cm is 0, and since stability of the aircraft has not changed, because we have not changed the configuration of the airplane, we have kept the CG same, we have not changed any shape of the outer surface of the wing, tail, vertical tail or fuselage, the same airplane. So these two lines will be parallel because these two lines represent static stability. These two lines represents what is the neutral point, and CG is same for both the airplane, both the configurations of flight. The same airplane I am taking from one CL to another CL. So these two lines are going to be parallel, and this is the new trim point where the airplane will be flying at thrust equal to drag, lift equal to weight, or it's a cruise. So what has happened? What is the charter of duty for the elevator in terms of some number? You see, nothing has changed between this line 1 and 2, but for the y-intercept. So this much additional Cm at CL equal to 0 has to be generated, or we say Cm at or Cm0 to be generated. And who generated this? This is generated by the elevator deflecting upward direction. Okay. If I now compare 1 and 2, we find additional delta Cm is generated. And who has generated this delta Cm at CL equal to 0? If it is a symmetric airfoil, it is equivalent saying alpha equal to 0. Who has done it? It is by the elevator being held in up position, right? So my elevator should be enough powerful to give me this much of delta Cm. If suppose the delta Cm is very large, and whatever you do elevator deflection, still it is not able to generate that much of delta Cm. So then you won't be able to trim the airplane for that CL trim. Okay? So that is where is the connection. And try to understand that via static stability. Okay. Let us take a simple case. This is Cm and again CL. This is one graph for the same airplane. This is second, 1 and 2. For the same airplane. So what might have changed? Why these slopes are different? Because even if the configuration is same, what we are agreeing that yes, we are discussing about the same airplane. So external configuration is same, but their dCm by dCl or the static stability parameter is different. That could happen only because the CG locations are different. You could very well see case 1 is slope, here you see slope here you see. This slope is more negative compared to slope at 2. That means the airplane in the configuration of XCG1 is more stable than XCG2, or I can also say if this is the neutral point of the airplane, if XCG1 is here, XCG2 is somewhere here, and so the difference between the XCG2 and neutral point is lesser compared to the difference between XCG1 and the neutral point. So I say this airplane is statically more stable than this airplane. No issues? Now let us start to see. If I want to trim the airplane at this CL star, if I have this airplane, that is the airplane with CG as XCG2, or which is statically less stable, then I have to see that this much of negative pitching moment I have to counter by generating positive pitching moment. And how will I do that? I will deflect the elevator up. So let us say that this corresponds to the elevator up 1, or this is I say 2 because as per this convention. Now same CL star, if I want to get it trimmed by aircraft 1, that is if I want aircraft 1 to fly at this CL star with lift equal to weight and thrust equal to drag, how much negative pitching moment will be generated is this much. Okay, that means I have to deflect elevator much higher compared to this case to nullify this negative pitching moment, and let's say that is delta again up, but it is 1, and delta up 2 is definitely less than delta E up 1. If I see from static stability point of view, please understand this concept. This aircraft is more in terms of static stability. It has a more static stability compared to this aircraft. That is why, because this is having higher static stability, I need higher elevator deflection to change its stream from one equilibrium to another equilibrium. So which is very obvious, and we can understand that any aircraft which is highly statically stable, it has an inherent tendency to come back, to retain in that position, to restore, and to have initial tendency to come back to the position. It will resist any change from that position very strongly as compared to an aircraft which is having static stability lesser. Okay? So this is very, very clear to us. So this understanding is extremely important, and we will be using this understanding to define a relationship between elevator required and the CL trim. Thank you very much.